Welcome to our. Today we'll be examining the physics behind a railgun and how it can launch projectiles without relying on conventional mechanics.
A railgun is a device that utilizes electromagnetic force to accelerate a projectile along a pair of parallel conducting rails, hence the name. This force is generated by a current that runs through the rails in the projectile, which induces a magnetic field.
First, we'll examine the theoretical working model of a railgun in more detail. Most contemporary railguns are still in development, but we can analyze the forces involved.
We'll also look at the model we built ourselves and a tracker analysis of projectile's motion in order to see how accurate our results were and to identify any factors that weren't immediately apparent. The ability of the railgun to accelerate a particle hinges upon two main requirements: the presence of a sufficient source of EMF and the ability of the particle to conduct current.
While the EMF is inherently required to create a current, the particle must also be able to conduct current in order to have a closed circuit. This closed circuit creates a magnetic field as the projectile moves away from the source of EMF.
The interaction between the current and the magnetic field creates a force that pushes the particle along the length of the railgun until the projectile reaches the end and is fired out.
However, if the source of EMF does not possess a sufficient magnitude to produce a powerful enough current, the force created can be too small in magnitude, and this can make operating the railgun fickle. This irregularity calls into question the conductivity of the rails and projectile, as they are also important factors.
Our railgun employs a slightly different method to accelerate our projectile, since the theoretical model requires a high-power setup and an early model proved irregular.
Since Mr. Roth also had called the ability of the railgun to sufficiently move the projectile into question, and had pointed out that the closed current itself would probably not be enough, we decided to supplement the force by adding magnets.
We were faced with two options: either to add conducting magnetic wheels on either side of the projectile so that we could use the force to induce rotational torque, or to add magnets near the beginning of the projectile's trajectory to supplement the initial force and grant it the necessary magnitude.
In the end, we decided to simply add magnets between the rails to augment the force and achieve the desired acceleration.
Our setup contained everything we needed for a working railgun: a battery to provide the EMF, tinfoil to create conducting rails, a rod of copper wire to act as the conductive projectile, and a cardboard for the base material.
We used magnets to increase the force, which wasn't an issue since neither the tinfoil nor the copper projectile were magnetic.
The rails are above and separated from the magnets, since we also needed to make sure the magnets wouldn't attract the alligator clips.
Putting together the railgun was fairly straightforward, as we only needed to account for a single force. Applying right-hand rule is also fairly simple. Lay your hand in the direction of the current and point your fingers up, since magnetic field is directed up between the rails. Your thumb should point along the rails, away from the battery.
After viewing the projectile's motion and tracker, we observed a constant acceleration within a reasonable degree of error.
This was what we expected, since our force, F, and our mass, M, are constant. Our acceleration, A, should also remain constant.
We ran multiple trials, and the railgun performed consistently enough for us to conclude that the constant acceleration we had observed wasn't just a fluke or a result of erroneous measurement.
Thank you.
Thank you.